Welcome all the participants. I welcome Dr. J. Krishnaiah sir. He's an assistant associate professor at IIITDM Kurnool. And welcome sir for this 5 days works FDP faculty development program on manufacturing and automation. Sir, I'm audible to you, sir?
Yes, you are audible.
Thank you, sir. So I will request our principal, sir, Dr. T.K. Das, to introduce our college to you, sir. Sir, principal, sir.
Good morning, learned
Good morning, sir.
faculty members. Arunachal, Jayaprakash ji, Ranjan, and our guest faculty. It's my privilege to again welcome you for the second day of this FDP program. Many of the attendees are outside our institute, so it will be good to introduce myself and our institute. Myself, TK Das. I joined RTC Institute of Technology in the year of 2019. Prior to that, I was working in Steel Authority of India Limited as General Manager Quality. This institute, RTC Institute of Technology, it a privately financed institute approved by AIITDM New Delhi and presently affiliated to Jharkhand University of Technology. This institute is located at a very picturesque place near Ormanjhi block at the bank of a water reservoir and slightly forested area. So environmentally and location wise, it's a very good place for education. The institute has a good infrastructure to carrying out programs, both degree and diploma. Presently, institute is offering 5 programs on BTech and 3 programs under diploma. 5 programs: civil engineering, computers science and engineering, electronics and communication engineering, electrical and electronics engineering, and mechanical engineering. The diploma programs are civil engineering, electrical and electronics engineering, and mechanical engineering. Recently, we got ISO 9001 2015 certified. We are also going for NAC and NBA accreditation. With this, I end my talk and wish all the best for the second day of the FDP program. Arvind ji. Arvind ji, can you hear me? Hello.
Yes, sir. Yes, sir.
Please start the program. If Arvindji is disconnected, Priyaranjanji, you can take over and continue with the program. Yeah, Priyaranjanji is also not getting connected.
Yes, sir. Some technical issue. Please wait, sir.
Please. Other attendees audible? They could hear me or not? Our faculty members?
Principal sir, do you hear me, sir?
Yeah, now I'm here. I can hear you.
Okay.
Could you hear me what I was talking?
Yes, sir. Yeah, now it's smooth, sir. Voice is clear, sir. So I hope everyone. Sorry for the interruption. Now I will introduce about Dr. J. Krishnaiah, sir. Actually, Dr. J. Krishnaiah, sir, is Associate Professor at IIITDM, Kurnool, Andhra Pradesh. Dr. J. Krishnaiah, sir, is Associate Professor in Mechanical Engineering Department. And previously, he worked with BHEL as a Senior Manager at Corporate Research and Development of BHEL, Hyderabad. Overall, he worked with BHEL, Trichy, BHEL Corporation R&D unit in various capacities for total about 9 years. At BHEL, he has been working on developing solution with application of a marine machine learning and deep learning for building cyber physical system of power plant and with a digital twin of subsystem twins of subsystems for modeling, control, and optimization. Before joining BHEL, he has worked in various organizations during 2005 to 2010 and developed AI ML solution. He is graduated in mechanical engineering from JNTU Anantapur, and he has a master degree and earned his doctoral degree in mechanical manufacturing science, manufacturing system engineering from IIT Kharagpur in 1998 and 2005 respectively. He has 8 international journals, 23 national international conferences, 12 patents filed, out of 4 patents and 8 are published stage, 3 design registration, 4 copyright registered in his account. So, sir, I will request Dr. J. Krishnaiah, sir, to continue the session. Dr. J. Krishnaiah, sir. Dr. J. Krishnaiah, sir, do you even hear me, sir? Krishnaiah, sir, can you hear me? Hello?
Yeah, am I audible to you now?
Yes, sir. Now you're audible.
Yeah, I think there was some audio problem. Now I think it is clear.
Okay,
Thank you for your nice introduction to the participants, and I also thank the management for allowing me to talk here in this particular FDP, and particularly I thank your management, your principal, and your HOD, and particularly I thank Dr. Arvind Kumar for inviting me here.
Thank you.
So shall I start now with this? I think you have to allow me to share my screen.
Yes.
Yeah, now it is enabled. Just let me start it. Are you able to see my screen?
Yes, sir.
Yeah. Uh, Good morning, all the participants, and good morning, all the organizers. Thank you very much to be here to listen to me here on this occasion in the FDP. As you know, the focus on the manufacturing has been there like for last 10 years, at least within India. Of course, there has been a lot of focus on the manufacturing elsewhere, and that's how some countries have progressed in manufacturing, and then they are loading into our country with lots of. I mean, I can say it's not loading; it is dumping, in fact. So here in this occasion. The application of robotics in manufacturing we will briefly touch upon, because in itself is a very huge subject to complete within 2 hours. So anyway, well, let us try to give a small introduction to the topic. So in this, I try to cover the introduction, glance through current scenario, Industry 4, particularly very much important, and maturity models of data analytics and the maturity model of automation. So why these two are covered, once we go through, you will understand. And then as a part of maturity model of automation, here I put self-driven car as a one of the example. However, the same could be applicable for the robots also. So just because everybody will know how the car works and how it will be in the terms of manufacturing. If you put manufacturing and traffic in similar analogy, then we will see how the self-driven car is a kind of robot. Okay. So what is a robot, in fact? That may be, of course, all of you are aware. Sorry, all of you are aware about it. However, just as a part of this particular talk, I would like to cover. A robot is a mission, especially one programmable by a computer, capable of carrying out a complex series of actions automatically. So this is the definition of robot. So a robot can be guided by external control device, or the control may be embedded within it. So external could be connected through wired or maybe through wireless, doesn't matter. And then the controller could be in cloud or maybe next to the robot itself. Okay, it is something like this scenario could be external, could be anywhere. the way, I mean, as long as you are able to access it, that should be okay. Wherever it is, it can be considered as one of the things. So robot may be constructed to evoke human form, but most robots are task performing machines. So this point we have to clearly understand. Most of the, I mean, common people, the robot means the human form of thing that can perform all the activities that human can do. But for the technical people like us, we know that it is the sequence of operations that can do, we call them as a robot. However, there are variety of forms, like for example, robot could be industrial form, and that is industrial robots, or if a robot in the form of human, that is humanoid robots, a robot that are a system that can autonomously perform, like maybe moving from one place to other place, do certain tasks, like for example, unmanned guided vehicles or automated guided vehicles, that is AGVs. That also, I mean, they are also like part of industry most of the times. And last but not least, the drones, they also can now can be considered as a part of robot, because robot, the definition, first definition, if you see, a robot is a machine, especially one programmable by a computer and capable of carrying out complex series of actions automatically. So the drones also become part of it. So however, in terms of manufacturing, to see how these robots can be usable or useful, we will see in this particular hour. So there could be some confusion in the robotics and robot. So robotics is a branch of engineering that evolves the concept, design, manufacture, and operation of robots. So here, the concept, design, manufacture, and operations. So all these four of robots, whatever that involves these four concepts in terms of robots, that we call as a robotics. The objective of the robotics field is to create intelligent machines that can assist humans in a variety of ways. So that's what we have seen, a variety of robots that are possible in the fields are in a way they are intelligent. So in the field, like for example, robot, if you want to define something, robot is a mechanical structure with intelligence embedded within it, or intelligence that is controlling it. So that is a robot, I mean, the other form of definition we can take it. So further, robotics can take a number of forms. A robot may resemble human, or it may be in the form of robotic applications such as robotic process automation. Again, here, this point we have to be clear on. For example, just a minute. Let me take pen. So here, the robotic process automation, here there is hardware part of it and software part of it. So here, the digital domain, whatever the process are being automated, for example, if you want to calculate or process certain data or collect certain data, or collect text, correct. All these are robotic process automation comes under that. Whereas the hardware, the manufacturing part of it, or all that are hardware part of robotic or industrial robotic applications. So the robotics now, this also becoming part of RPA, also becoming part of robotics, which simulates how human can engage with software to perform a repetitive rule-based tasks. So how do we do repetitive works? Copy from one column to other column, or do certain multiplication of two columns, things like that. How we do is also performed by an automated tool that we can call as a robotic process automation. So keeping that in view, so why at all we need robots? So why we need robots is, if you want to see the batch size versus the manufacturing unit manufacturing cost. So cost of one unit to manufacture, and then the batch size, if you see, if it is a manual, the cost will be continuing to be there same way. In fact, as you need more and more people, if there is any difficult in getting human, then that becomes in fact difficult. In fact, after some time, the availability of labor, if it is difficult, then it may increase also. But however, here it is given like this, so let us consider as it is. So it is constant. If it is a numerical control method, then also like it will come down to certain time, to up to certain amount of size or batch size, and after that it will be stagnated. So here transfer line is another method where where robotics comes into picture. So where the cost will continue to fall down, of course, up to a bigger size. But however, application of this transfer line manufacturing need certain minimum batch size beyond below which using this batch production or manufacturing purposes is not useful. So for this purpose, we need robotics to be there in the manufacturing, and that's how we can reduce the cost per unit manufacturing. Okay. So here other why we need robots is another way is, suppose you have a hazardous environment where human may not able to actually access it. So earlier people were having some kind of master slave mechanism kind of thing where there will be a barrier between hazardous environment and then where human operator is working. So here this is master and this is slave. The human operator will be operating this robot, and then here this manipulator will be replicating the activity that human operator is doing and then performing this activity. However, recent days, because of autonomicity of robots, even the human operator requirement is reduced. In fact, it need not be like visually nearby. This person could be sitting somewhere else, and remote process automation also is active nowadays, right? Even we have seen recently one driver is sitting at home and then operating the crane. which is maybe 500 kilometers away from his home during the COVID seasons. So, which means now if the communication or whatever the signal the driver or the operator is giving, if it is immediately possible to reach there, that is with now currently 5G kind of networking, so the remote process in real time is possible. So this is the second reason why we need robots. Another reason is where unexplored planets, for example, this is one Mars rover where human have not seen at all, but where the robot has reached there and then mapped the entire area through the robotic or autonomous vehicle ways. Like for example, here this autonomous vehicle will have a multiple sensors, and then where the sensor data is sent to the station, and then where the map is built based on the sensor data, and the location is estimated through that map, and then the robot is controlled if required to navigate and then do certain activity there on it. So this is again a remote operation where lakhs of kilometers away, the Mars rover on the Mars, the rover was being operated from base station on the Earth. So keeping this in view, suppose let us understand the type of configurations of robots, because those are the whatever situations we have seen, but each situation may be possible to perform by certain kind of robot. So here Cartesian robot, it is a simple planar, that is XYZ axes, it can move linearly. So there is no any rotation here. This is up and down, this is back and forth, this is also back and forth here. So XYZ are being operated. So here in this slide I have given certain videos also, I mean links for the videos where the explanation of this particular configuration is also given. So we will touch upon them once. So another is there is one rotational element and then two linear elements which makes a cylindrical robot. So cylindrical robot where this base is rotational element and these two are the linear elements. So with that also it can perform, and then the work, yeah, here the I forgot to mention, this is a workspace. This particular robot can reach out. So within this cuboid, anywhere this particular end effector can reach. This is the end effector, so this particular end effector can reach within this cuboid. Whereas in this end effector can reach a cylindrical workspace. So because it can rotate 360 degrees and then up and down, back and forth. So this is the minimum and this is maximum. So cylindrical workspace is what possible. This is a spherical robot where we have multiple rotational elements and then multiple, in fact single translation element. Of course there could be multiple translation element also, no problem, but however with these three elements, that is two rotational and one the linear, that makes a spherical coordinates or spherical workspace we can achieve with this kind of robot. Another is a SCARA robot kind of thing, not SCARA, is articulated robot where here this is rotational, this is also rotational, this is also rotational, this is also rotational. So all rotational. So it is articulate, this is called articulate robot, where the workspace is spherical again, but it has different than this. The reachability is more in this particular configuration. So we have further, if you see the articulated robot, that is last one we have this cylindrical robot, how it look like. This is Kara robot, how it look like. So this is linear, first one, whatever you have seen. This and this, the gantry robot and linear robots will be having a cuboid workspace. This will be having spherical, this will be having cylindrical. There is another robotic type called a parallel robot, or we can also call this as a delta robot. So where all these links are parallelly available to access the or to manipulate the end effector to reach the different locations. So if you want, actually, let us now we may be wonder like how this position of the end effector we will be able to calculate. So I would not be like touch upon all these within this class, but I want just to give a brief exposure here so that you are aware how it is calculated. For example, let us say we have 3 joint robot we have, where if you want to calculate the planar kinematics for this, so that is for knowing the end effector position, that is xe and ye. So if you see, if you want to know, suppose assume that the 0th joint or first joint is at 0 position, and then based on that that is our origin. If you consider using origin as a initial position, if you want to find the position of xc and or position of end effector, that is represented in xe and ye. So here we have got an equation. So let us see how these particular equations have come up to find the xe. Suppose let me put the pointer just a minute. So here we know this is x-axis, right? So if you want to know the position of this one, and then this one. So if you want to calculate the length of this, we know theta 1 here. So we have in a normal trigonometry, if you use, this is length of this, that is L1, and then cos theta. The L1 and cos theta, if you multiply, you will get this distance. Because this link length we know, and then theta also we know. So to calculate this length, we have this L1 into cos theta 1. And then if you want to get this distance, so we have L2, that is link length 2, and then theta 2 also there. But this theta 2 is with relative to link 1. So that is, in addition to theta 2, we also need to add theta 1 to find the distance. So this distance we will be knowing. So this to find this distance, L2 into cos theta 1 plus theta 2. So that is theta, this is theta 1 plus theta 2 will get this length. Now we want to find this distance, then it is, now we got this theta, and then we got this theta, and then we got theta 3. So theta 1 plus theta 2 plus theta 3 or cos theta 1 plus theta 2 plus theta 3 into L3 will give us this distance. So we got entire distance now with this respect. So this is how we will be calculating x1. Similarly, for y, that is this and this and this height, or this height, this height, this height is what we have to calculate. So here to calculate this, this is L1 sin theta 1, and then L2 sin theta 1 plus theta 2 will give us this distance, and then L3 sin theta 1 theta 2 plus theta 3 will give us this distance, and totally we'll get this YE, right? So this we got XE and YE together, and that's how this is forward link calculation, we can say a forward position calculation we can do for this particular simple link, I mean 3-link robot. Of course, as the complication increases for the robotic arms and robots, whatever we have seen here, the method will be accordingly will be changing from one method to another method. So here whatever we are seeing is for the Cartesian things, right? This Cartesian, based on Cartesian coordinates we are calculating. Suppose when we want to calculate so generally what happens, we may want to track certain path. Let us say we want track certain path like this. So from this to this, if XE by E has to change, then what should be the theta 1 and theta 2, theta 3 will be changing from position to position is what we may be interested in, because it is not that where it is going based on the link length we need to calculate. However, our interest would be generally to have certain track and then access it or rotate the motors accordingly to reach or track that particular line. So that is our more important. So from the forward calculations, we may have to find inverse calculation, which means to reach this XEYE one position, what should be the link length or link rotation to be done for link 1, what should be the rotation for the link 2, what should be the rotation for the link 3 has to be calculated. So that is what called inverse kinematics. So inverse kinematics, for example, here let us say I am giving just one particular wrist position, how we calculate this theta to reach. For example, here let us say this is our end effector, that is XE and YE. We have already seen how to calculate that. Suppose what should be the rotation of wrist, this is link 3, if we want to see, so that what should be the position of this particular wrist at this point, so that it's with this XE and theta 3 it will be reaching this position. Suppose here X W and YW, if you want to calculate XE minus L3 cos the phi E. So phi E is this total so from horizontal how much angle it is making, this is what taken, and then subtracted from this. So cos theta phi e will give what is this position. So from that position we are calculating this position, right? So that is xw we got. Similarly yw also will be getting the same principle. That is a trigonometric method, and then we'll calculate this. So this is how, I mean, the simpler, I mean, the positional or rotation of each joint will be calculated and then tracked back to the lowest angle and lowest joint, and then keep doing that activity. So for this, whatever the computation needed to be done, all that will be done through inverse kinematics method, and then the torque, the rotation speed, and then all that for each motor, and all that will be done by a controller. That's what we were talking in the beginning. The controller could be embedded within the robot, or it could be external also, but still it can perform that activity based on information provided by the controller. So the controller part we may not touch upon here right now, but however, so keeping this right now, how the calculation of the position is done using forward kinematics, and then calculation of the different positions needed to be performed to achieve the end position, how we do through inverse kinematics we have seen briefly. Now keeping this in mind, suppose let us see how these are used within the robotic applications. So here I have put some pictures, but in here, if you see in this particular thing, KUKA industrial robot operating a foundry. So this robot is operating as a operator, that is that person is standing in front of the furnace. So it is loading the jobs and then taking back the jobs based on the requirement of whatever the programmed way it is done. So this is KUKA robot. However, whatever the precautions that need to be taken in terms of maintaining the accuracy of robot link length and all that will be done here. Okay, so another is here another robot here, Baxter, a modern and versatile industrial robot developed by Rodney Brooks. So here we are not able to see much here, but however it is operating the computer itself. Okay, so this is the manufacturing unit of cars, how the robots are being used to do assembly process and as well as the fabrication process within the manufacturing line of cars. So we have one video also in this. We'll see if time permits. Of course, we have to see few of them. So one, we'll bring it here. So another example of robots in assembly. So here this robot is assembling the wheel with the tube and tire and tube here in this particular case. And similarly here it is this another robot actually performing some activity on the electronic board. Here the simulated environment is being shown in manufacturing, typical manufacturing line. Here the virtual reality based controller for the robot is given in this particular case, where this human operator is controlling this robot through goggles here, which is seeing what the robot is seeing in real time here. Here there is another environment where a collaborative way of doing activities in the manufacturing. is shown where two robots are working together with the human operator, where certain operations that are complex maybe currently not possible by the robots are being done by human, and then certain activities are repetitive activities that need to be done accurately and fastly, so that those are done by the robots. So here have some visuals. Some you can use. I mean, you can use these links later. But however, few I would like to show here as part of this, so that certain load is reduced on me to explain certain things. So here, why the human operators or why robots are needed in the industrial environment? If you see, are you able to see this?
Yes,
Hope
sir.
you're, yeah. Right. I'll increase the speed so that yeah. So that was about like intelligent robotics in the manufacturing environment. So here in the industrial 4 environment, if you see, please excuse me if some videos are required. That's why I have put here. So let's see this. This is one more. Yeah, last one. Uh, Yeah, there are few more. However, we can have a look at them later. Particularly, there is a video on how the car is manufactured in BMW. I think it is there within this list. Okay, you can have a look at it. It is total 14 minutes video on how it is being done. So let's move on the further. Why do we need intelligent systems or robots? Particularly robots, as we defined earlier, robots are considered to be intelligent, should be intelligent enough to be considered as a robot sometimes, and the recent definition has changed that. So here, why do we need intelligent systems in the manufacturing perspective? If you see, one is to predict uh, what happens to the existing systems. So in a way, the each and every equipment will meet certain definition of robot definition that we have just seen, which will be monitoring themselves to see when any failure will come into picture. So here, if particular sensors and conditions based analytics are being done for one particular equipment within the factory, then we call that as a pilot asset. If a series of those equipment being monitored and then in a line, that we call a product line, and then within that factory, if all the product lines are monitored and then assessed, that we call as a factories. So this kind of factories, if multiple factories are together uh, monitored, then we call that as a cognitive automation. So here, the cognitive automation level, if you want to reach the total, the manufacturing units, all the at company level, it has to be automated, and then that's what makes a complete automation of the activities within the manufacturing. Otherwise, line-wise product line, if one product line is automated, maybe line may be producing accurate products, but other product lines may lose on that. So, Industry 4 concept, and that too, here previously, whatever we are seeing, each line may be customizing one particular requirement. If you want mass customization in that sense, customization reduces the production speed, whereas mass customization, if you want consider and then move on that, then that leads to mass customization. So mass customization means suppose if 100 different customers are there and then all their requirements are different, still if your manufacturing unit or the company able to address all their requirements, then that is one level of customization we can say. But suppose you have 1 lakh customers and then all their requirements are all met personally to their requirements, then we call that as a mass customization. So to achieve that, the Industry 4, or other way called Fourth Industrial Revolution, has become one of the key area, key methodology to achieve a key way of doing things. So I think most of you would have been seen this kind of slide earlier, where the difference between Industry 1 to the Industry 4, how the progress has happened. However, along with that, as we are moving from Industry 1st to Industry 4th one, the complexity or the degree of complexity of the systems also increasing, because the amount of whatever the monitoring, you can say, are predictive or diagnostics requirements, you can say, are predicting their maintenance, you can say, are prescripting what to be done if you want to achieve certain thing is also achieved here. So there is a complexity, and as well as to lead or to address that complexity, the intelligence of the systems also increased, or the other way to say, the usage of AI or artificial intelligence has increased in the manufacturing area as well. And then that's why the people now say that cyber physical systems, that means in other way, there is a interaction between cyber system and the physical system, means digital system and the physical systems interactions have increased to achieve or to address the complexity of the system here. So how this complexity, or this, if you want to see in terms of how these are achieved, if you want to see in terms of data analytics, that we will see, and how the operators role has changed from industry 1 to industry 4 is depicted here, where the operator 1, if you see, it is more of manual and dexterous work plus machine tools and manual operated machine tools. So here the human operator has to be engaged all the time to derive work out of these machine tools. And then there should be a person who will be monitoring all these workers. So that means that the supervisor also needed to be there to keep the production activity intact. So that we call as a operator 1. So this has lost up to 1960, we can say, where all the operations are manual, and then the machine tools also only mechanical systems. Next came into picture, that is numerical control systems into picture, where computer-aided design, computer-aided process planning, computer-aided manufacturing, that is CAM, tools have come into picture to address the to use the numerical control systems and then operating systems all together. So in addition to that, enterprise information system also came into picture, that is databases for all these are available. So with this assisted information, if the worker is doing some activity by sitting here, then we call that as a operator 2. So where control room are next to the mission tool that we have, that is controlled by numerical control systems, and then he will be programming that computer which is attached to that particular equipment. So this is what we call as a operator 2, and then which is in between 1960 to 1970. However, if you see in our Indian scenario, I think this role is still continuing. So this operator 2 is still continuing in the most of the MSME and then small workshops. So in even 2020, which means around 60 years, this we are continuing. Of course, we would have not started this 1960 itself. We would have started somewhere, maybe 1980 or somewhere. From 1980 to current, that means 32 years, still we are as a operator 2 level only, where the numerical control systems are more employed in the organizations or manufacturing systems. So certain companies, of course, here in the world scenario, if you see 1970 onwards, there is a shift in the manufacturing scenario where the robots have come into picture, where a cooperative work with the robots and machine tools and computer tools. Here, I don't see, or I don't say that this is a cooperative work, but the robot was doing certain activity and then human operator was doing certain other activity, where virtually there was a cooperation, but they were not together because these robots were in cages earlier, thinking that there could be harm to human operator. So that was the fear. In fact, in the industry, it was there. Even now, also it is continuing to be there for some more time. I think we'll have other fear later. That is different. But here, the operator cooperative work with robots, mission tools, and computer tools. If you see, it lasts for 30 years in the world scenario. That is 70 to 2000. Of course, the Industry 4 scenario has started only in I think 2008 onwards, sometime here, sometime 2008 or so it started. But operator 4 has started much early, somewhere here, and it is continuing to be there, where you have different tools, robots to assist the operator. So work aided by machines. That is human cyber physical systems. So cyber physical systems are assisting the operators to perform the activity, which means the one operator will be using all these equipment to perform the activities there. So this is human cyber physical systems point of view, we can say. So so this is what the role change of the operator change, and then that's actually the reason why the importance of what you can say robots in the organization has increased. So to achieve that, or to actually implement all these, it is not just a one-day job, or it is not just okay. We thought to achieve this and then we implement. It is not possible for it like that. So for that, the background work, if you see, there are many. So here, in fact, it's not today, it was yesterday, we should say, like where all human operators were doing things to achieve, that is operator 1 or operator up to 3 levels, we can say, where in the Industry 4 scenario, where you have robots that are being performed, and then the operator is here, and then to monitor them to do the activity, where the knowledge base is sitting outside to actually prepare a better work environment here, and then operator is only one who is operating all these things. So so what is enabling Industry 4 is along with the autonomous robots, there are many things. This is not actually this is not exhaustive list anywhere, but because we are interested in robotics, so robotics also a part of the Industry 4. It's what and it's not just one robot, it should be automated guided vehicles to complex, the robots that are able to perform complex activity also involved as a part of autonomous robots. So to achieve all that, this is a point I was trying to mention. So the activities that are possible to achieve, it is not just came overnight, but it was possible only through incrementally developing the activities. For example, descriptive analytics or data analytics. Under data analytics, we have 4 different ways of doing analytics or using the analytics in information, and that is here the maturity model 1 type. Here the automation and then human involvement are the action that is being performed with robots, and then human involvement in doing certain action is depicted here, where with the descriptive analytics will give you what happened, and then there could be large amount of human involvement is there to take decisions and then do certain action. So that is the scenario of the descriptive analytics. And then diagnostics, why it happened, why did it happen, will be done by the diagnostics, which means it's kind of post-mortem. What happened if certain equipment failed, then why did it fail is what is possible to analyze through data and diagnostics analytics. Then where the human operator or human involvement is little reduced compared to the descriptive analytics point of view, and then decision again human is being taken here, and then action is also performed by them. So predictive analytics is the next level. What will happen? Suppose if you want to do this particular, if you continue with this particular control parameters, what will happen will be given by this predictive analytics. In other way, suppose if with a certain speed and certain depth of cut, if certain tool is being operated, when that particular tool will fail can be assessed by this kind of activity analytics, that is predictive analytics, where human intervention is reduced further with minimal intervention here, and then completely done by the database, whatever the data that is collected through sensors, all that the data driven system will be taking care of all the activities, and then decision again by the human or the system that is being done. So the system, data driven system and the human operator will lead to a certain decision. Together will lead to a certain decision and then do certain activity. So under prescriptive analytics, we have again here we have two subsystems. One is a decision support system, another is decision automation system. So prescriptive system will give decision support at a one maturity level to where the decision will be taken and the action will be performed. Whereas this decision automation is completely by system itself, where based on the data or situation currently it is there, the action is suggested automatically. There is no human intervention in the prescriptive analytics anywhere. So completely system driven. The decision may be supported by human in this case. This human support is needed here to continue the action, but whereas here to continue the action you don't need a human support. You can continue and then perform the activity. So that is data analytics maturity model 1. So why we are talking about this in the robotics is basically how robot intelligence has improved over a period of time from maybe the point when the robots have started to the current generation robots, how the improvement or intelligence has improved is one background thing is this data analytics that is being used to achieve that kind of the activity. Next we have one more maturity model. It is basically the complexity. As complexity increases or the difficulty increases, the value also increases here. So here in this particular case, if you see this is sorry. So here same descriptive analytics to prescriptive analytics. If you see the complexity or difficulty to perform that has increased. but at the same time, the value that is actually provided by that analytics is also increased with the as it moves. So here it is only information, here it is leading to optimization. Here it is in insight, that is information, some kind of insight. Insight means there is some more information is hidden from this, certain information is available, whereas insight is further more detailed information about the why certain things happened is given here in the diagnostics. Foresight is futuristic, like what will happen, and if you want to make it happen, what we have to do is done by these two. I mean, this what will happen will be done by predictive analytics, and then how we can make it happen is descriptive analytics. If you want to achieve certain things, what kind of parameters to be tuned so that you will achieve that level, right? So this is a maturity level. So keeping that, whatever the Industry 4 operator, Industry 4 concepts and operator role change concept, data analytics concept, data maturity model concepts putting together, if you see how the automation is able to achieve, we can see here. So why do automation levels matter? So automation level help to introduce AI and grow its complexity in stages without excluding users or losing their trust. So that is important. So you cannot overnight completely automate the industry, but with time, as we add more and more insight to the existing knowledge or add more knowledge to the existing knowledge, then we can go into complete automation. As we know, the automation that whatever we are saying in terms of where the usage of robots compared to 40 years or 50 years, there is a lot of difference. The extent of automation and maximum desirable automation level is always defined by the customer. The customer has to give his requirement. He cannot suddenly move. For example, let us say 3 years back, some MSME has procured some CNC tools, vision tools, to perform their activities, whatever they are. And suddenly, if you go today and then ask them to go for computerized vision tools with Industry 4 connectedness, then it may be difficult for him to do all the change immediately, because he has not revived or he has not received whatever investment that he has done. He has not received his profit from the investment, whatever he has done. So what is achieved is first start him with a minimal automation that is possible, keeping the existing tools without replacing them. So add-on will help. So that's how the automation level has to be achieved, and that's why the automation level matters, to have different solution for different people. Suppose if some company has invested 20 years back and now they are looking for replacement of existing vision tools, then they should go with more or high level automation straightforward, because if they invest on old, then investment may be waste compared to whatever they could have been achieved with the current things. So here user level 0 is no automation. That's what we have seen in the operator 1 level. If you see, users complete all aspects of task manually, but might be notified about certain events or changes by the system. So in addition to whatever the operator level we have seen, in addition to that, the operator is getting the information about certain events. For example, certain system is failing, so that information will be given to the customer directly. So it's kind of, you see, in the data analytics point of view, it is kind of descriptive analytics, where you'll get the data. I mean, you'll be monitoring about what has happened. That's it. What has happened, you can monitor. So users can also call on assistive functions to verify or prove their work. So this is a level 1 automation, where the operator will be doing all aspects of tasks, but he will be knowing if certain things happen within the tools. Level 1 automation is basically assisted operation. So the system actively supports the users by suggesting or recommending possible solutions. So it is something like in between diagnostic analytics and predictive analytics. If you see, this is the level that is both diagnostics analytics and predictive analytics are being used here as a level 1 automation, where the system actively supports the user by suggesting or recommending possible solutions for action. Then if you see level 2, partially automated. So the system actively evaluates and prepares suitable solutions, but leaves their execution to the user. The user has access to all the relevant information and must edit to create the data manually. So here you see this aspect, which is very similar to this level. Prescriptive analytics, decision support is what being done by that. So decision, all that decision will be available at the disposal of human, but human will be taking action to taking decision to do certain activities. So that is what the level 3, level 2 partially automation level, and level 3 automation is fully automated. The system actively evaluates, presents the solution, which then just need to be reviewed and approved by the user. The user is still the verifying instance, but is not execution operator. So here, in highly operated thing, like he will be programming codes, all the decision, that is at prescriptive level plus decision support, prescriptive level, decision support level itself, but activities performed by the automated system, that is robot itself, not the operator. Operator will not be performing anything. He will be the verifying authority, he will not be doing any activity. So he will be only a verifying authority, or is kind of approval agency. So that is highly automated systems. That is level 3. Level 4 is fully automated. So where you can say prescriptive analytics, last one, that is all the activities are performed. Decision automation is also performed, action also performed. So this is what the level of this fully automated systems. So here, so AI has a full autonomy within the boundaries of its tasks and operates independently. So within the boundaries, so certain mission tool is given to it, and then it knows in and out of that particular mission tool, and then it will be operating independently without human intervention. A human operator is only consulted if error or conflict arises. So if any error or conflict arises, then only human operator is expected to be there to verify that. Nevertheless, all actions and decisions must be transparent, traceable, and reversible for human auditors. So this is where certain kind of, hitch is there currently, where the now the AI is getting transformed into explainable AI, where this transparency or traceability or reversible for human auditors is possible. Otherwise, if explainable AI is not there, why certain things have happened may not be easy to trace it. So the transparency and the traceability and reversibility will be missing if normal AI is used, because most of the AI techniques that we deal with are black boxes or gray boxes. In the sense, we know little bit of it why certain things have happened, but they are not white boxes. So we cannot reverse back why certain error has occurred in the automation due to AI involvement. So that is very difficult to do that, and that's where the explainable AI will save us in addressing that, and then in successfully meeting the requirements of human auditors. So these are 4 levels that we are seeing in the automation. And then we have seen 4 levels of operators, and we have seen 4 levels of data analytics. Keeping that all in view, the self-driven car concept is not just self-driven car alone, but now it is actually becoming important in automating certain things. For example, if you want to have a plant that is self-operated plants, or let us say a drug discovery, or let us say a material discovery is happening. If that is required to be done, then the robotic systems need to be there, and AI need to be there to achieve that activity. So you would have seen recently, even DST has rolled out one thing called material acceleration, material discovery acceleration plan, or the framework, where they have involved many institutes as part of that. Of course, now it is under the evaluation state. They had evaluated multiple levels, and then there are 3 teams, 3 groups. The groups are formed by different institutes, have identified, and then the final evaluation is being happening. So here I would like to inform IIITDM Kurnool is also one of the institutes to be part of one activity there, where material discovery acceleration plan is going, and that is what called MAP. So under that, this activity is going on, where the robots and AI will be the one of the things. So the drug discovery or material discovery process, if you want to automate, there also we need some kind of self-driven car concept wise only. So to keep the generality are easy to understand, here I am taking the car as a one equipment where we want automate the fully autonomous way. So here, if same whatever we have seen the automation levels, here if you want to map similar ways, of course there is some mismatch in terms of levels there and here. Here we have 6 levels, there we had 5 levels. However, doesn't matter. Here there is some kind of overlap here it is more divided. So here 0 level, level 1, level 2, level 3, level 4, level 5, where in the level 5, steering wheel is optional. Optional in the sense you don't need steering wheel for the car. Can we imagine that we don't need steering wheel for the car is a kind of level of automation that is possible to achieve, or already some companies have achieved. They are experimenting on the roads. The similar way, the industry automation or the manufacturing processes can be automated. Maybe you would have heard a old joke. If I mean, when we call a fully automated industry or manufacturing unit, is that there will be one operator who is looking or monitoring through video or whether all equipment are working in condition or in properly or not, and then to switch on and switch off of those equipment if required is one person will be sitting and monitoring from the control room, and then next to him there will be a dog which is sitting to control the person not to stop or not to touch the button. So which means that is the level of automation. In fact, this was actually narrated by my Guruji. There is our PhD guide who was telling this is the automation that we want to achieve. So he was telling 20 years back during my PhD time, and that's what now becoming a reality one in the industry. So that was the kind of automation the people have expectation. So here level 1, level 0, if you see, automated system issues warnings and may momentarily intervene, but no sustained vehicle control will be given to the system that is controlling the vehicle. So that is at the 0th level. So what is needed to achieve at 0th level? If you see, monitoring of various vital points of vehicle, that is the vehicle condition, 4-tube air pressure, fuel tank, brake condition, etc. all need to be monitored, and then if any of these things are malfunctioning, then a alert or a warning has to be issued to the driver so that he will take certain action. However, at the same time, it may also take momentarily control over the vehicle, but again immediately the control will be given back to the human operator or human driver. So that is the what level 0 level automation. So what does that mean is that currently whatever vehicles or four-wheelers that we are driving are level -1 or even less than that, because all these conditions are not there, right? I mean, we have to check whether air pressure is there in all tubes or not. We have to check whether engine is in condition or not. We have to check whether fuel is there or not. Of course, there is a fuel tank measurement or the meter will be available, but it will not alert you. Even if even one drop petrol or diesel is there in the tank, still it doesn't alert you. It will be only more showing you, that's it. And then brake condition, nobody will be telling you whether your brakes are in good condition or not. So that's why we call that whatever -1 level, whereas this 0th level is kind of where we'll be knowing what has happened. So it is kind of descriptive analytics kind of thing, where the system will be monitored for different parameters, and then those will be alerted or displayed to the user to take appropriate action, right? So next is level 1, if you see, where hands-on, which means the steering wheel is still in the control of human operator. The driver and the automated system share the controls of the vehicle. Example, are system where the driver controls the steerings and automated system controls the engine power and maintain a set of speed. So here the speed is controlled by the automated system, but the steering is controlled by the human driver. So that's what the share-based control between human and automated system is achieved here. Or the engine and brake power to maintain very speed. So this kind of adaptive cruise control is adapted here. And then parking assistance will be also given where steering is automated while speed is under control of human driver. So here in the parking level, the speed is controlled by the human driver, whereas the steering is controlled by the automated system. See the difference. So there is an exchange in the control in this particular case. So the driver must be ready to take over full control at any time. Still, in this case, the driver must be ready, which means is not only just controlling the steering during the cruise or normal driving, and in reverse the speed and the steering also you should be able to take care. So suddenly if something comes, he should be able to immediately react on it. So lane keeping assistance, that is type 2, is further example of level 1 self-driving car. So the automatic emergency braking feature, which alerts the user to a crash or deploy full brake capacity, is also level 1 feature. So here sudden brake also assisted by the self-driven cars at the level 1 with the with the automatic emergency braking system. So when we move on to level 2, if you see here, hands off means you don't have to keep your hands on steering, which means the steering control also is taken care by the automated system. So the automated system takes full control of the vehicle, that is accelerating, braking and steering. All three activities are done by the automated system, and the driver must monitor the driving and be prepared to intervene immediately at any time of the automated system fails to respond properly. So which means though he is hands off, he has to be ready to take care of or to take the control on the vehicle. So in shorthand, because this is hands off, is not meant to be taken literally. So this is what though it is a hands off, we say, but still you should not take literally. Momentarily you can take off your hands from the steering, but you should still sit in front of the steering wheel and then be ready to take over. So contact between hands and wheels is often mandatory during SAE2 driving. So here some kind of some kind of guidelines are there under SAE2 to driving to confirm that driver is ready to intervene. So this is in between momentarily we need to give that condition, meet that condition. So that is at level 2. So here now you're only just sitting but ready to act on. You're sitting in the driving seat, but you're not always controlling the vehicle, but you are ready to control the vehicle anytime. So that is level 2, and then level 3 is eyes off. So here the driver can safely turn their attention away from the driving tasks, but that is the driver can text, watch movie and things like that when he's sitting in front of steering wheel. The vehicle will handle situation that calls for an immediate response like emergency braking. So here this up to this level it can do. The driver must still be prepared to intervene within the some limited time. So still it has to be on the driving seat only available and then be ready for taking any action within some limited time specified by the manufacturers when called upon by the vehicle to do so. So vehicle may give you attention alarm to take over and you should be ready there. So still you are not out of the driving seat, you are still on the driving seat alone. Next is level 4, that is a mind off. So similar to level 3, but no driver attention is ever required for safety. That is, driver may safely go to sleep or leave the driving seat. So this is the first time the driver is leaving the driving seat. So self-driving is supported only in limited spatial areas, that is geofenced areas. So here we need to understand geofenced areas is the area within which these cars are allowed to be in self-driving mode, but otherwise on other zones the driver has to sit in the driving seat. Outside these areas or circumstances, the vehicle must be able to be safely abort the trip, that is park the car if the car driver is not taking control over it, which means even if he is not on this driving seat, but the vehicle will stop and then wait for the driver to take over, but otherwise it will not stop. I mean it will not move from there. So that is level 4, mind off. Next is level 5. As I said, steering wheel is optional. No human intervention is required at all. An example would be a robotic taxi. Here, robotic taxi where it will be running on the roads without any human intervention. So if this perspective, if you take on the manufacturing, so in fact manufacturing area is more protected than the road. So if any vehicle self-driving is achieved autonomously, there is even possibility that in the industrial environment this autonomicity is possible to achieve, and then in some country, some industries it is already done, right? So with these 5 levels, keeping in mind all the whatever data analytics operator levels, all that we could see the correlation of automation, robotics or robotic activity and data analytics and industry 4 into one thread, right? So if you have any doubts, we can explore or address that. There are some here. There are some references I have given. Of course, all other references are at their own slides, but some have not kept. So I have kept lost some references and some videos we have here. Right. So these videos will give you more information which I would have missed in this process. So any questions?
Thank you, sir, for your.
Dr. Arvind. Yeah.
Yeah. Thank you, sir, for your very wonderful lecture, very informative lecture, sir.
Dear participants, if you have any question to sir, please ask. Topic is very informative about robotics, and sir has dealt very beautifully, starting from forward to inverse kinematics, the um, end effectors motion, then the application of robotics in industries, then industry 4.0, and so overall the lecture is very informative. If you have any kind of doubt, please put forward to the sir.
Any questions or any suggestions?
Any question, any
or
suggestions?
what
Yeah.
improvement can be done here
Yeah.
to give a better talk? Of course, I understand here right now we could not touch upon more details of how the robotic calculations or inverse kinematics and forward kinematics can be
Yeah,
done, because it is
huge-
difficult to handle within this
Yes.
2 hours.
Yeah, it's a huge
So I
thing.
gave just a brief.
Yeah, that was needed, sir. That was needed, very brief itself, but it was informative. And